With that, I don't have a recap really on the board today because I'm going to start a brand new topic. We are a little bit behind. I was checking out where I was last year at this time, and I was already kind of in 11.5. So I'm a little bit behind. I'll try to catch up today as best as I can. If I really feel it's a problem, I may make a video and have you watch it and take some notes on it outside of class. But let's just see if I can get caught. It won't be a lot of catching up to do, but there's just a little bit I might ask you to do. So I'd like to do something really quick. I need some volunteers for a little activity. Do I have any? I need like five of you. Can somebody let me know if they'd like to be volunteer? Let's see. So this is a graph, drawing a graph now. Jose, Marcus. Oh, you guys are gonna make it easy on me. Can I get Kevin? And anybody else want to volunteer? Mason. Sorry. The graph's gonna get too big. Okay, so I've got vertices for each of you. Then over here, I'm going to make some other dots. Blue, green, yellow, and white. Okay, and now I have to go around to all of you volunteers and I have to ask you which of these colors you like. So Lindsay, I'm going to start with you. Of these colors, and you can like all of them, none of them, or any of them in between.
Yellow and blue.
Yellow, blue, and white. Yellow, blue, and white. So I'm going to draw an edge between colors that she likes. So blue, yellow, and white. Lindsay likes those. Okay, Jose, which of these colors do you like, if any?
Green and white.
Green and white. Perfect. And Marcus, which of these colors do you like?
Blue, green, and white.
Blue, green, and white. Awesome. Kevin, how about you?
Blue and green.
Blue and green? Blue and green. And Mason, how about you? Blue and green also. All right. So I'm drawing this messy graph that is basically connecting two vertices if it's a person and a color that they like. What we have just drawn on the board, my friends, is an example of a bipartite graph. A bipartite graph is basically a graph where you can split the vertices into two camps. And I will often do the camps in the following manner. I will put like diamonds around, all of the vertices from one of the camps. So everybody who's a person who was a volunteer would have a diamond on them. And then in my other camp, I would label those vertices with a different notation, maybe a circle. In this case, those different colors. And the key thing to notice here, guys, is that when I've split these vertices into two camps, there is never an edge between two circles, and there's never an edge between two diamonds, right? So two vertices that are in the same camp cannot have a vertex, that cannot have an edge between them, right? There's no edges connecting anything over here, and there's no edges connecting anything over here. So this is basically what a bipartite graph is. Now let me write down kind of a formal definition. Right next to this picture is a good place to put it, I think. So I'll write down the definition of a bipartite graph. So let's let G, which has a vertex set and an edge set, V and E, like usual. Let's let that be a multigraph. Okay, I'll just remind everybody that a multigraph does not have loops. So we're not going to allow any loops here. We're just going to have possibly multiple edges between the same vertices. Now, we wouldn't have that for this example necessarily, but it's just a multigraph. So we call G bipartite. Bipartite if we can find subsets. And I'm going to call these subsets capital X and capital Y. These are just subsets of the vertex set V. So if I can split up my vertex set into subsets X and Y with the intersection of those two subsets should be empty. So there should be no vertex that's common to both of them. But if I take the union of the two subsets, I should get all of the vertices in the graph. So this is what I mean about splitting up the vertices into two camps. The camps are the X and the Y, and there's no common vertices in those two camps, but together every vertex is in one of the camps exactly, okay? And every edge, little e in capital E, has one vertex in capital X and one vertex in capital Y. So that is a bipartite graph. And we have a nice example of one on the board here. Maybe another example. Another example of this, I'll draw an actual picture here. So you can see, by the way, that lots of things in the real world would be bipartite. You could have, instead of colors, you could put social security numbers, or anything else that's like associated, that you could associate with a person. Hair color, eye color, what state they're from, anything like that, and you would have a way to draw graphs that look like bipartite graphs. Here's another one. Maybe we have a graph that's just like a 5 by 5, sort of a mesh. This is kind of a mesh graph, so it's gonna look like it's got 5 rows and 5 columns. Let me just get all my dots on here first. Okay, so we got kind of like a 5 by 5 grid, and then what we do here, guys, we just connect everything up with horizontal and vertical edges. So this is kind of a nice example of a bipartite graph. Let's get these vertices showing up a little bit better. When you're drawing graphs, guys, if you're doing them by hand, try to make your vertices nice and thick dots, so I can clearly see what's a vertex and what's maybe just a stray mark or something like that. But if I gave you this graph, and I could ask you, is this bipartite? A good way to actually answer that kind of question is to just start, it's kind of a foolproof process. Just start somewhere, let's say in the upper left corner, and let's maybe circle the vertex at the start. Anything that vertex is adjacent to has to come from the other camp. So I could put my little diamonds around those. And then anything that's connected to a diamond has to be a circle again. So we would get circles in these vertices here. And if you are able to go through the whole graph without getting into a jam in labeling these things, then your graph is bipartite. So as you can see, I'm doing pretty good here. I'm alternating between the circles and the diamonds, going all the way through the entire graph, labeling my vertices. And anything that's next to a diamond becomes a circle. Anything next to a circle becomes a diamond. And I am able to go all the way to the end of the process. Does that kind of make sense? So this is a bipartite graph. And what we have shown here is actually what they would call a bipartition. It's a bipartition. All of the circle vertices are in so capital X would be, the set of all of the circled vertices, and capital Y could be the set of all of the diamond vertices. So you could actually break it down into those two camps. By the way, when you kind of draw it this way, it's an interesting question. Suppose you're teaching a class, you've got 25 students, and you got them sitting in 5 rows of 5. The question would be, can you make everybody move to an adjacent seat, either to the left, to the right, in front, or in back, and take a new seat? Like, could you take your 25 students and ask everybody to get up and move to a seat that's next to where they're currently sitting? And it may seem like a hard question at first, but actually, when you realize that 13 of your students are sitting in the circle camp and 12 of your students are sitting in the diamond camp, you understand that having everybody change to a different seat basically means they're switching camps. And so the 13 students that are currently on the circled positions would have to fit into the 12 places where you have the diamonds. Which, by the pigeonhole principle, would not be possible, right? If two people are gonna not share a seat. So the answer is no, you could not have 25 students just all get up and move to an adjacent seat. Even though, you know, you might think that could be possible if you didn't have it kind of laid out in this manner. So I think it's kind of a neat idea as well. The classic example of where bipartite graphs cannot exist is going to be when you have cycles that are of odd length. Even this graph right here, just that is not bipartite. And it's a simple picture, but if you try to, start with a circle somewhere, and then you say, oh, everything connected with a circle has to be a diamond, well, but then you get two diamonds that are connected, right? So this is a no right here. So you can't do that. So there is actually a theorem to this effect, which I'll state in a moment. But before I do that, well, actually, I can just go ahead and do it now, I think. I think I'm just gonna go ahead and do it now. I think we've already got enough up here that I can state the main theorem about this, theorem 11.4.1. So we're gonna have one sort of main result in this section. Yeah, Jose?
We allowed it to be free, but that just be like a tripartite thing? Or no?
If you wanted to create 3 camps instead of 2, is that what you're talking about? So yeah, if you had like X, Y, and Z, and then there was no intersection of any of those, but their union was the whole thing, and edges had to go between different camps, that would be called a tripartite graph. Yes, actually, you'll see that in, I have a question on one of the sample tests that's about tripartite graphs. So I'm not gonna talk about them here, but you certainly can generalize this, absolutely. You could do k-partite graphs, for that matter, where you have k different kinds of camps and no edges can connect within each of those camps, but all of the edges go across to different camps. Yeah, you can definitely generalize this. Okay, so here is the theorem, guys. A multigraph G is bipartite if and only if all cycles within G have even length. Even length. So you're looking at this, you see a lot of squares, a lot of cycles of length 4. You could make longer cycles and go around the entire exterior of the whole picture. You'd have a cycle of length 16, but they're all even length here. Whereas here, you've got something of odd length. It's not bipartite. So I think it's, at least with these examples, it's kind of reasonable. Let me see if we can do the proof of this. It's kind of a nice one. Does this seem reasonable to everybody? It just means that if you find even one cycle of odd length, then your graph is not bipartite. Another thing is if the graph has no cycles at all, then it is bipartite because the condition will be vacuously true. If there are no cycles, then of course all cycles have even length because you don't have any cycles. Yeah, so so this is, I think, a pretty reasonable result. Let's see, the proof. So we have to go forward and backwards on this. Let me just talk about the forward direction just a little bit. And I'm gonna explain the forward direction essentially in contrapositive. So if G contains a cycle of odd length. Right, so in other words, if this was not true, if G did not have all cycles of even length, so if G contains a cycle of odd length, then it cannot be bipartite. Now, I'm basically so far, all I've done is stated the contrapositive of what we're proving here, but it cannot be bipartite because, I'll give a quick reason here. Assigning adjacent vertices of the cycle to opposite sets, and this is X versus Y that I'm talking about from the definition, results in an impossible situation. Basically, you get two X's together or two Y's together. I don't like to do. I mean, we could make this very formal. We could set up our camps like this. Here's my cycle. Let's say it has length 2K plus 1, right? So, you know, 1 edge, 2 edges, 3 edges, and so on. So you have an odd cycle here. This is my odd cycle. And if you now just go around and you say, well, X1 will be in the diamond camp, and then X2 will be in the circle camp, X3 would be in the diamond camp, and so on. What happens is you get all the odd ones to be in the diamond camp. And so that last edge is violating the rule there that you have to have one vertex from each camp. So this is the problem. Does that kind of make sense? In other words, it's not just for the three, not just for a 3 cycle, but for any odd cycle, you're gonna run into that same problem. Yeah, go ahead.
Could you use the result that if you have a function from an odd size, let me use one next point. To itself, yeah. A function from an odd set to itself should always have a fixed point.
I don't know about that. I mean, if I have 3 objects, I can permute them to 3 different positions. It's still a bijection.
Oh, yeah.
So, I know what you're trying to think of, but I'm not quite sure how to formalize that. So, yeah, basically, this is it, right? You set up your camps like this, but the problem is that, so all the even ones are in like the circle camp, all the odd ones are in the diamond camp, but these 2 are both in the same camp and there's an edge between them. So that's the problem there. Okay, so that's really the idea behind the forward part of the proof here. Yeah. That makes sense to everybody? Is that good enough? It's a little bit casual, but I think it's good enough. Okay, let's do the backwards direction though. Backwards direction is kind of interesting. For the backwards direction, we are actually gonna prove that directly. We're not gonna do a contrapositive. We're just gonna say, yeah, let's suppose that all the cycles have even length. Let's prove that G is bipartite by actually creating the bipartition with X and Y. Okay, so let's see if we can do that. So let's assume all cycles in G have even length. Okay. And we may assume that G is connected. what that's really just saying is, if you've got like, you got some kind of graph here, and then over here you have some other graph. Whatever, right? If you wanna make a bipartition of the whole graph, you might as well just tinker with it one component at a time. Now, what I did here was illegal, but anyway, you get the idea. You can sort of create your bipartition here, create your bipartition here, create two camps in each of your components individually. You know that there's no edges going across the components. So you won't run into any problem by sort of taking the union of the vertices that are in the two camps for each component. See what I'm saying? I mean, this is how you would do it if I gave you a disconnected graph and I said, show me how to bipartition it. You would take just one component at a time and do your circles and diamonds on that component, as if the graph was connected, right? And then you say, okay, now moving on to the next component, let me do the same thing. In none of those components could you have any cycles other than even length. Because the whole graph has all of its cycles of even length. So you can apply that assumption component by component. So by applying the reasoning below to each connected component of G, sort of in isolation from all other components.
You say like subgraphs?
Yeah, it would, each connected component would be like a subgraph of G. Yeah, that's definitely a fair way to say it. Okay. So I'm gonna assume that G is connected by applying the reasoning below to each connected component of G, if that's all right. Okay. Now, here's what I'm gonna do. I'm going to select any, actually, let's just use a different word. Let's just say fix any vertex V in the vertex set. So just start somewhere in your graph, right? And then what I'm going to do is I'm gonna create my two sets. So maybe I start with blue here. And that's my V. And now I'm gonna create my two sets as follows. I'm going to let capital X be the set of, I'll call it little x in V, such that the shortest walk, so I'm talking about a walk in the graph now, so following a sequence of edges, the shortest walk from X to V has even length. Okay, so I'm going to create for capital X the vertices whose shortest walk from V has even length. So like, for example, blue is a walk of length 0 away from blue. Okay, so this would be in capital X. What else has an even length walk? How about the walk from blue to yellow? Right, blue to yellow. So this one has a shortest, there is no walk of length 1 between blue and yellow. So the shortest walk has length 2. So that's an even number, so yellow belongs to capital X. Right? The shortest walk from blue to, I guess we don't actually, the shortest walk from blue to green looks like it's gonna be at least 4. Because you can't go, oh no, I'm sorry, I can go down to Mason and then up to green. So sorry, that's also 2. Right? And same thing with white, it's gonna be length 2. So these are all forming capital X right here. Whereas the walks from these vertices to this side are all gonna have odd length. And you probably have already figured out what capital Y is gonna be. It's gonna be those vertices where the shortest walk to V has odd length, right? So let's just add that now. Capital Y. This is gonna be the set of, I'll call it little y this time, just to make it nice notation. Such that the shortest walk from Y to V has odd length. Right. Okay. Well, let's just note that the intersection of these, can you have a vertex that its shortest walk to V is both even and odd? That really doesn't even make common sense, right? I mean, there is a correct number for what the shortest walk is, and it's either an even number or an odd number, it's not both. So this is definitely empty, I don't think it needs a lot of explanation. Okay, I'm kind of checking off my definition here, right? And if we took the union. So would you agree that every vertex? Okay, remember, G is connected, so I'm able to walk between any two vertices. So there is a walk between any vertex in V to little v, and therefore there will be, either a shortest walk of even length or of odd length. I don't know which one, but for sure, every vertex is either here or here. Now, if the graph wasn't connected, we might have a problem right now, because there could be a vertex that you cannot even walk to little v. And so there wouldn't be a shortest walk of even or odd length in that case. That type of a vertex would not be in the union. But if we're assuming G is connected, we don't have that problem. Yeah, okay, great. So we got those two things. Now what else do we need here? Oh, every edge has to connect a vertex from X to a vertex from Y. So let's talk about that. So I'll make a little claim here. It's the last part. The claim would just be something like this. No edges exist between vertices in capital X. So there's no edges that are just within X, and then I'm just gonna say, we won't actually write out the other case, but I'm just gonna say similarly for capital Y. So we'll just argue it for capital X, and then we won't bother to basically repeat ourselves for capital Y. So let's try to justify this claim. I'm gonna give the reason here. This is the last thing we need, is to just explain that there's no edges connecting vertices in X. So let's suppose that X1 and X2 are both in capital X with an edge, which I'm going to denote as this set X1, X2 in E. So I'm kind of going by way of contradiction here. I'm kind of going at it by way of contradiction. And one thing you might notice in the proof so far, guys, is I actually have not used my assumption. I haven't. The assumption says something about the cycles in G. Nowhere in here am I even mentioning cycles. We're just talking about walks, right? So this is gonna be a contradiction, because it's gonna mean that I could make a cycle of odd length in G. That will contradict this first line of my assumption here. Do you see how I can do it? So X1 and X2, they have this edge here. But see, I can start, so let's just do it. We can construct a cycle of odd length, excuse me, contrary to assumption. And that will finish the proof of this claim. Let's just write down what the cycle of odd length would be. I guess I can just do it maybe right here. What I can do, guys, is I can walk from X1 to V in an even number of edges. So I can take X1 and I can do a walk. I'm just going to write this as dot, dot, dots here. This is an odd length, right? And then I can walk from, this says from Y to V, but of course that's the same as walking from V to Y, just in reverse. I have a, did I do something wrong? Oh, this is supposed to be even.
Yeah.
Okay, yeah, something was not working out there. Yeah, that's an even one. Sorry about that, guys. The X1 is in capital X, right? So that's an even walk. And then from V, I can walk back to X2. And this walk is also even. And then I have one more edge that takes me from X2 back to X1. And that is obviously length 1. So you can see that the total length of this cycle is some even number plus some other even number plus 1. That's odd. This is a cycle. We started and ended at the same point. So it is a cycle, but it has odd length. We just constructed that. And that's contrary to the assumption that all cycles have even length in this graph. Does that make sense to you folks? Look okay? Everybody with me on this? Yeah, okay, so that's the theorem. That's really the main theorem about bipartite graphs. It all comes down to kind of just looking at the cycles. Looking at the cycles, yeah, that's it. Okay. So far, so good?
Could you explain it maybe one more time?
Yeah, absolutely. What I'm doing is I'm kind of doing this last bit. Well, actually, so just to back up, we've got all this stuff in the definition here. We gotta find the subsets. So I wrote them down here. I just created them. I gotta check that their intersection is empty. I gotta check that the union is all the vertices. So that much I just made a note of. And then this is the last thing I have to verify, right? That every edge goes from a vertex in X to a vertex in Y. Right? So I'm doing that by way of contradiction. I'm saying that I want to show that you cannot have any edges just within X. And also that you cannot have any edges just within Y. What would that leave you with? The only kind of edges that you could have would be edges that go between the two vertex sets, the two camps. So this claim would be basically explaining that box, if you're with me. But I'm proving the claim kind of by way, this is kind of by way of contradiction, if that helps. I basically have said, oh, suppose that you actually do have an edge between two of the vertices that are within X, right? And then what I did is I created the contradiction by making a cycle of odd length. Even just one cycle of odd length is going to contradict this assumption here. And is it pretty clear how I did this? I pasted together. I sort of pasted together two, so you got your vertex, what was it, V here. Yeah, I created, here's an even length path from X1 to V. And then I came over here and I did some other even path from X2 to V. And then I just made one more edge there. And now I actually have an entire cycle of odd length. Sometimes a little visual doesn't hurt, right? That's kind of how it would look.
That makes sense.
Yeah, does that make sense to everybody? Yeah, Marcus?
It wouldn't matter that like maybe you could somehow repeat a vertex. Just I guess for example.
If you're talking about shortest walks, right? If you were repeating vertices while you were doing these walks at all, then you probably aren't doing the shortest walk because you could take, I think we had this in one of your homework problems where you had to like remove little subcycles where, if you visited a vertex more than once, you could just extract like some of those edges. So I think all of that kind of potential snafus have been kind of removed from the
But like
problem.
going from X1 to V and then going back to X2, maybe you use some of the same vertices.
Oh, I see what you mean. You're right. So some of these, so there could have been a pinch point here, maybe where there was a common vertex.
I don't think it affects the logic of the.
I don't think it does actually. Yeah, I think that although that might be possible, it should not affect the fact that like what if like this last one here was like that. So x1 to v looks like that, and then v to x2 looks like this or something. That's kind of what you're
Yeah.
talking about? So if that happened, then it's a good point. Like, in that case, you know, however many edges are here and how many edges are here should have the same parity at least. So,
I guess you could say a cycle is a closed walk on the assumption and then just make it based on that.
yeah, yeah. Let me think about that, whether that's actually something that would be needing to be explained a little bit more. Yeah, because in this case, maybe I can't walk to x2 or to x1 without going through that vertex, so you actually would have a cycle created there. But so somehow, if you did this, you can see I've made a cycle here and also a cycle here. One of those is probably gonna have odd length, and you'll get your contradiction out of that smaller cycle, I think, but that may be something that needs to be addressed. Huh, I've not thought about that. Good point. Okay, I'm gonna leave that for now. Let me just make one last definition, and then I think we're gonna move on to the next little topic here. This next little thing is just, I wanna talk about the complete bipartite graph. There's gonna be probably some homework problems on this, so I just want you to be familiar with this. Let's say I take two numbers, m and n, that are both at least 1. Then the complete bipartite graph. So you all know what the complete graph is, right? Graph where you have all possible edges among the vertices. So this is similar. This is a complete bipartite graph. And this is denoted k sub m comma n. So now we have two subscripts, right? Consists of sets x and y with the size of x equal to m, the size of y equal to n. So we make our two subsets and they have sizes m and n. And every edge possible between capital X and capital Y is present. So basically, wherever you were allowed to have an edge, you do have that edge. So, right, and of course, no other edges. It's still gotta be bipartite, so you won't have any edges within X and you won't have any edges within Y. Okay, so, for example, the one that we sort of jotted down here in the beginning, this would not be a complete bipartite graph because there are some edges that are missing. Litzy does not like green, for example, right? So that edge is not there, but if everybody said they liked all of these colors, right? Then it would have been a bipartite graph. So that's just an example. And so you can do things like figure out how many edges this graph has. Obviously, the number of vertices is m plus n. But then how many edges is it? Well, you can probably, maybe we'll just do a quick example. You can do the handshaking theorem, for example. If I wanted to write down, for example, k of 4, 3. So you would draw, you know, your first camp here, that would be the X, capital X, and then the second camp would have 3 vertices, maybe over here. And then you're just gonna draw every edge that you have, right? So the first vertex goes to all 3 of those, the second one does the same, the third one does the same, and the fourth one does the same. We have all of those edges. And, you know, you can kind of figure out, well, oh, every vertex on the camp on the left has degree 3. And every vertex on the camp on the right has degree 4. And those 3 and those 4 are obviously related to the 4 and the 3 here. And so now you can use the handshaking theorem and figure out how many edges you have. If you add all of this up, you have 24, right? So the sum of the degrees of the vertices here adds up to 24. That's going to be twice the number of edges by our handshaking theorem. And so then the number of edges in the graph is just 12. It's 24 over 2. It's just 12. So you can probably figure out where the 12 comes from as compared with the k of 4 comma 3. So I'll leave it at that. Actually, what gets much more interesting is, this is something you can start thinking about now. Which of these KMNs are going to actually be planar? In other words, drawable with no crossings. So this one has lots of crossing edges in the middle. You can see that. We know that there's no edges among this camp and there's no edges among this camp. So you might think about what scenario on M, and it turns out there's a very simple answer. And I'm going to come to it, but I'm probably going to make you sweat it for a little while, right? There's a very simple answer for which values of M and N would give you a complete bipartite graph with a planar representation that you can actually draw it as a planar graph. That's something to think about, and then we will actually have a theorem on that when we get to the next chapter. So, but for now, that's all I'm gonna say.
Something with K, right?
It starts with a K? Yeah, something like that. Okay, let me come back over here. This was good. You guys did this little thought experiment with me of this bipartite graph really well. That was a nice example to look at. So I appreciated that. Okay, I want to, in the spirit of keeping up with where I want to be by the end of today, I'm going to move right along and talk about the next section. The next section is about trees. So 11.5 is called trees. And this is just a special type of graph. And there are, so changing subjects all of a sudden again. There are many different ways to define what a tree is. And they're all equivalent, so we just have to pick one. We have to sort of pick one to be our definition, and then we'll try to convince ourselves that all these other ideas are equivalent to it. So a tree, by definition, is a connected graph. So it has to be connected. That becomes disconnected. So it's a connected graph that becomes disconnected if we remove any edge. Does anybody remember what did we talk about something like about this? If you take a connected graph and you remove an edge and it becomes disconnected, what did we call that edge? It's a bridge, right? It was called a bridge. So this is just another way of saying, so let me just say that is, a tree is a connected graph where every edge is a bridge. That's just basically rephrasing the definition. Every edge is a bridge. Let you guys catch up. I know I'm writing kind of fast. Okay. Maybe I'll draw just a quick example of something that is a tree. So it could be, your good old classic stick figure. Something like that would be a tree. If you remove any edge from this picture, it would no longer be connected. So there has to be a way of walking from any vertex to any other vertex, which there is here. But if I remove an edge, any edge from this graph, I will probably isolate a vertex, or if I don't do that, I at least will split it into two different connected components, and I won't be able to walk between the two components, right? So this is a tree. This is a tree of order 1, 2, 3, 4, 5, 6, 7, 8, I guess. I have 8 vertices there. So a fun little problem is to figure out like all of the isomorphism types of trees of certain orders. It's kind of an interesting thing. So if you had 8 vertices, how many different trees could you draw? You know, so the usual thing, you can go through and, oh, this graph has 1 vertex of degree 4. Obviously, here's a tree that has order 8. That is not isomorphic to that one. Right, because I have a vertex of degree 7. But again, if I remove any of these edges, I will disconnect the whole graph again, right? So those are 2 examples of non-isomorphic graphs of order 8. I do think that there is a homework problem coming up where they do ask you to draw the isomorphism types for graphs. I don't think it's order 8. I think it's 5 or something like that. It's a smaller number, but that'll be a nice little exercise. Let's see. There's a couple of other things to notice here. So maybe an example of something that's not a tree. This would be something where it's possible to remove an edge and still have the graph be connected. And actually, for that to happen, what you need, let me just draw, maybe I'll try and make it have order 8 again. You do something like this. So there's a graph of order 8. And some of these edges, when I remove them, they would disconnect the graph. But if I remove any of the edges that are kind of around this square, even if I remove that edge, I can still walk from this vertex to that vertex. I just have to go the long way around. Actually, I'm going the long way around a cycle. Guys, you want a really good way to say what a tree is? It's just a connected graph without any cycles. It's another way of saying about it, of saying the same thing. So just a quick remark. A tree is a connected graph with no cycles in it at all. So if your graph has cycles, it's not going to be a tree. Yeah. It's basically when you have a graph that's a tree, it basically looks like a skeleton. It's like everything is connected together, but just barely. You can't remove anything from it or you disconnect this graph out. So it tends to have fairly few edges. In fact, there is a theorem about that. You might wonder how many edges there would be. You don't want to have too many, because if you have lots of edges, then it's more than likely that some of those edges are removable without disconnecting the graph. So there is a theorem to this effect, and it goes something like this. A connected graph of order n is a tree if and only if it has, well, actually, let's just see, how many edges do we have? In this tree, how many edges are there here?
7.
It's like 7,
7.
right? How about in this one?
7.
7. This one's not a tree. How many edges do we have here?
8.
8.
So
Okay, so what do you think the answer is over here?
N minus 1.
And -1 edges. Yeah, exactly. It has to be exactly one less edge than the number of vertices. So a connected graph with n vertices will be a tree if and only if it has exactly n-1 edges. That's gonna be the theorem. That is gonna be the theorem. Okay. So, let's try and prove this. This is a little bit of work to actually write it up. But it's a nice result to be able to use, you know, because you can just count the edges if you want to, and that's gonna tell you what you have. So let's let G be a connected graph of order n. Right. We'll start off with a graph of order n. And I'm going to actually make a little lemma here first. So, sorry, I'm kind of doing this within the proof. So I'm gonna like make an observation that is within this proof, and then we'll go from there. So the first one is, the lemma is that G must contain at least n-1 edges. So a connected graph. So I'm not even talking about a tree yet. I'm just talking about any connected graph. Right, maybe over in the margin of your notes, if you want to have a little running example, like you just pick a value of n, start off with, 5 dots. And if I ask you, how can you make this turn into a connected graph using as few edges as possible? Right? Every time you draw an edge, you at least like connect something. So like I could add that edge, right? And then I could add that edge. And then I could add that edge. And then I could add that edge. But see, every time you add an edge, you have the potential to cut down on how many different isolated components you have. You start off, right? You start off this process. I think everybody probably understands the intuition of it. It's just writing it down. You start off with 5 separate connected components. And every time you make a new edge, you merge 2 of those components into one, right? So the number of components is now down to 4, right? I have this one and then 3 more individual points. And then I draw another edge, and that reduces the number of connected components. Again, now it's down to 3. And then I make another edge, and so maybe I connect these 2. Now I'm down to 2 components. Now, if I'm not smart about it, I might say, oh, well, let's connect that. That's true. That did not actually reduce the number of components because I drew an edge within the same component, which actually created a cycle, right? Trees are not supposed to have cycles. But anyway, so the number of edges that you will end up with if you want this to be connected is at least n-1. It could be more if you connect things together that were already connected by a different path. So let's just write that down. So for the little, I'll just call this little proof inside of this lemma here. Start with n isolated vertices. Meaning no edges whatsoever. So imagine you start off with a scenario where there's absolutely no edges. And then I'm basically just going to say what I was just demonstrating here, which is that each time we add an edge, each time we add another edge, the number of connected components if I add an edge to the graph, then the number of connected components of G goes down. So when I add one more edge, the number of connected components goes down by 1 or maybe 0. If I connect something that's already connected, then my number of components won't go down at all. So I'm gonna say it goes down by at most 1. And you're trying to get from n isolated vertices down to a connected graph. A connected graph, by the way, has how many components? If it's already connected? 1, right? It's just one. So if I'm trying to go from n down to 1, and every time I add an edge, I can knock that number down by 1. I'm gonna have to knock it at least as many times to get it to go all the way down to 1. Is this making sense? I'm trying, still getting over my cold. Sorry. Okay, so that's basically the idea. So what did I say here? So to go from n components to a connected graph, right? A connected graph meaning one component requires at least n minus 1 edges. That's our lemma. That's our lemma. Okay. That's the lemma. Great, so with that lemma in mind, now I'm coming back to the actual proof. Nothing I said here has anything to do with the tree. This is just connected graph. How many edges would it have to have? Okay, it's gotta have at least n minus 1 edges. So let's try to kind of now go to the main proof. So this is kind of the end of this little lemma. Just put my little box here. Let's see about the main part of the proof now. Give myself just a little bit more room. So let's try to prove this forward direction. And I'm gonna do it by way of contrapositive, meaning I'm going to assume that my graph does not have n minus 1 edges. Now, we already know that it has at least n minus 1 edges. That's a given. So if it does not have n minus 1 edges, then it must have n or more edges, right? So let's assume G has n or more edges. And again, I'll just say C lemma. It has at least n minus 1 edges, but if I'm doing the contrapositive of this forward direction, I'm going to assume that G has n or more edges. Okay, in that case, then when I was doing that process of adding the edges, at some point, I created an edge that did not knock down the number of components. Which means I was connecting something that was already connected.
Mhm.
Right? Which actually means I'm making a cycle in my graph, which trees don't have. I won't have a tree. But I'm gonna prove that this is not going to be a tree. Yeah, I just need to write it down, right? Okay, so then, at some point. It's a lot of writing today, sorry, guys. These are just kind of wordy, we just have to kind of spell these things out. Some edge joins two vertices that are already in the same connected component. Right. This edge that we just talked about, this edge that joins two vertices that are already connected is not a bridge. It's not, it's an edge that you can remove, but by removing it, you're not disconnecting the graph because those two vertices were already connected. Okay, so this edge is not a bridge So G is not a tree in this case. So this is kind of, you probably will get this right, but just so it's kind of easy to remember, we're doing a little contrapositive argument on that forward direction, right? That's kind of how that's working. That's not so bad. It's not so bad. Okay, what about the other part of this would be, well, if my graph does have exactly n-1 edges, then it must be a tree. Right, well, this is just basically saying that every time I added an edge, I did knock the number of components down by 1. Right, because otherwise, if I added some edge and did not reduce the number of components, then I wouldn't have been able to start with n isolated vertices and get it down to a connected graph with only 1 component. So every edge must connect 2 vertices that were not previously connected. Meaning that that edge is a bridge. Every edge is a bridge. That's what a tree is. Okay, so let's just write that all down. It's basically just another little couple of sentences, right? So in this case, each edge must reduce the number of connected components by 1. So each edge is a bridge. If you remove that edge, then you would have increased the number of components. You would have disconnected the 2 vertices that are incident with that edge. And if that's the case, then that would be a bridge. So G is a tree. Well, let's just say so every edge. Yeah, each edge is a bridge, so G is a tree. Yeah, I'm ready to say that. A tree is basically a connected graph where every edge is a bridge. We've already got the connected graph as the assumption. And now every edge is a bridge. So that's it. That's basically it. Okay. Yes, there's a whole bunch of little theorems here. Let me write down a couple more theorems. We have 5 minutes left or so. Is that about all? What was it?
I don't know if you mentioned this, but is every tree planar?
Ah, that's a great question. What do you guys think? Would every tree be planar?
Yes.
Yeah, you should be able to like lay out your stick figures, you know, in such a manner that you don't have to have any crossing edges. Those crossing edges are generally only forced if there's actually like cycles within the graph. And this kind of a graph will not have any cycles at all. So you should be able, you don't have that many edges to begin with compared to the number of vertices. So it's actually quite natural to expect that you could give a planar representation to all of them. But yeah, that's a really good kind of question to be asking, is like, how do trees connect with the other concepts? Another one would be a tree is, well, actually, so hold on, before I get to that. I was about to say a tree is always bipartite. And remember that bipartite graph, we had the theorem just a few minutes ago, a bipartite graph is just a graph such that all cycles have even length. How many cycles are you seeing in these trees?
0.
Not any, right? That's actually my next theorem, right? A tree does not have any cycles, and if it doesn't have any cycles, then by our earlier theorem, it's a bipartite graph, always. Yeah, so this is theorem 11.5.4. I'll just get this one down and then maybe one more, and then we'll be just about out of time. There's just a whole bunch of different ways of describing what a tree is. Okay, so here it is. Let G be a connected graph And remember, guys, if the graph is not connected, you can still just work with each connected component individually, and that connected component will be connected, and then you can apply the theorem to that, right? And sometimes you can just do that for each connected component individually, and taken all together, it proves something about your whole graph, even if it's not connected. So what I'm trying to say is this is not a horrible assumption. This assumption does not like limit our ability to draw a good conclusion here, because we can always just reduce our graph down component by component by component. And what this is gonna say then is, then G is a tree if and only if G has no cycles. Okay, and I'm gonna write a proof of this. This one is much shorter. Thankfully, this does not take nearly as much writing. And in fact, we're going to prove both directions simultaneously through a series of equivalences. So I can do this one really fast, right? So this one just says, G is a tree if and only if. So here's my proof. The first step is basically to just write down essentially the definition, which is that every edge is a bridge. And that in turn, I guess I need to erase this so I have a little bit more space here. This basically just means that every edge is going to be not part of any cycle. Because if you're on a cycle and you remove the edge, you have not disconnected anything. You've seen that before. So this is just saying that every edge is not on a cycle. Well, if every edge is not on a cycle, then you just don't have any cycles. Okay, so this is just G has no cycles. So there's your full proof right there. That's it. Okay. Does that make sense? All right. Pretty straightforward. One last theorem I will write down, and I won't prove it today because I only have like a minute left. I just want to state one more result because we're on a roll with this, and I think you guys will believe this even if I don't prove it. I'll prove it maybe during our Zoom class next week. By the way, next week I'll probably have a big puffy on. You'd be lucky if I'm not wearing a stocking cap because I teach out of the garage of my house in Colorado, and it is cold up there in the mountains. So don't be surprised if I look all bundled up, even if it's hot down here in LA. But we'll maybe prove this one next week. Let's see. So theorem, what is it? 11.5.5. I'll just state this for now. I think you guys will believe it even before I prove it. This one, we just have to say, let G be a graph. We don't actually need to assume that it's connected because that's going to be kind of buried as part of the conclusion here. So then G is a tree if and only if. So I'm going to give you yet another way of thinking about what a tree is, and I'm sure you're going to believe this. Namely, if and only if every pair of vertices X and Y in the graph, I'll just say in G, technically I mean in Z, but I'll just say in G. Every pair of vertices X and Y and G are joined by, now for the graph to be connected, there has to be a walk between any two vertices, but the thing about a tree is that that walk will be unique. There will be only one way of walking from any vertex. Go back to the stick figure that we drew or any of those other graphs. There's only one way. If I give you two vertices, there's only going to be one way to travel through the graph between them. So there is a unique path. So this word unique is kind of the key point here. There is a unique path that joins X and Y. I'm sure you know how the proof goes. I'm not gonna write it out today because I'm out of time, but you're going to, how do you prove something's unique? Assume there's two of them. Okay, here's the first one. Here's the second one. What did I just create? A cycle. A tree is not supposed to have any cycles, so you can't have two different ways of doing it. Okay, anyway, I just did the proof. We'll write it down better next time, but for now, that gives you the concept of it. Guys, thank you so much. I hope it made sense. Are there any questions? All right, we'll call it a day for today. I'm headed down.